Okay.
So let us see what a convolutional neural network is, how it is different from a regular neural network,
Yeah.
and how they are able to extract certain intricate patterns in data,
Okay.
why they are so powerful.
Sure.
So if we see a general or a regular architecture of a fully
A
connected
neural
neural
network.
network, we call the regular neural networks as fully connected layers, fully
Yes.
connected neural network, because
Yes.
every neuron in one layer is connected to all the neurons in its previous layer.
Previously.
So
Hmm.
if you take a simple MNIST database, we have 28 pixels in height and 28 pixels in width.
Hmm.
So that makes up a total of 784 pixels.
784
Yes.
pixels.
And all these 784 pixels are responsible to determine what image it is.
What image it is? Yes.
Right. So now when we, in reality, we may not need all the 784 pixels because each pixel may not really contribute
To
to that
the
image.
real image. Yeah.
Instead, maybe those images, those what I can say, pixels that
Mhm.
form a part of this particular shape may be really very important.
Yes, exactly. The only pixel which are in the digit, like digit 5 or 6.
Exactly. And primarily to say the edges of that particular digit
Yes.
are more important to us than the rest of the other
Sorry.
image.
Hmm.
No worries. So it is important for us to really pick out these images, these pixels
Okay. Okay. Okay.
from that image.
Hmm. Hmm.
Okay. So now, like this particular part of extracting the key features is called as feature extraction.
Okay.
This is called as feature extraction. Okay.
Okay.
We have certain classifiers which does feature extraction for us, like the Hog classifier, which is a histogram of oriented gradients.
Mhm.
We have LBPs, which are called local binary patterns. These
Mhm.
are all certain algorithms that do this exact thing for us. So
Okay.
we
Hog and
provide it.
LBP.
Yes, Hog
They
and
do the
LBP.
feature extraction actually.
Yes. So like we provide an image. These
Mhm.
these algorithms extract the key features and return the key features as a vector of numbers.
Okay.
That's what these classifiers do. Okay,
Return it as vector of
of
numbers.
numbers. So
Okay.
like maybe you can say those numbers that are available here are the pixel intensities of that
Okay.
particular patterns maybe normalized after
Mhm.
they are normalized, right?
Okay.
Like
Okay.
that. But now and then once these features are extracted,
Hmm.
they are once again passed through a fully connected neural network. So each and every extracted feature like this
Mhm.
pixel here is now a feature for our neural network.
Okay.
So
Okay.
now the
Okay.
entire image is not a input or image, but
Mhm.
from that entire image, the features are extracted, key features are extracted,
Mhm.
and those
Mhm.
key features are represented as vectors. And now these vectors are passed to our neural network, okay,
Okay.
in this way, in the similar fashion, like how we do.
Like a normal neural
Like a
network.
normal neural network, exactly. Like a fully connected neural network, and we get the output of what that particular. So here in this case of a handwritten digit, we have
Mhm.
10 classes. So now it will tell what is the probability of the first class, second class, third class, and so on. So the rest of the stuff is common. The only
Mhm.
difference that we are seeing from a regular neural network
Mhm.
to what we can say as an advanced version of the neural networks is this feature extraction.
Okay. Okay.
And this feature extraction is done by certain algorithms,
HOG and LBP.
LBPs. Yes,
Okay.
they do the feature. We have multiple other algorithms as well. These
Okay.
are some
So
common.
HOG, LBP are basically called algorithms.
Yeah, feature extraction
Feature
algorithms.
extraction algorithms.
Algorithms. Yes, but now then there was another question again.
Okay.
So why we should define those algorithms? We are defining it, right? So which part to detect, which part like to see where there is a more light or in intensity. That is something
Mhm.
that we are defining.
Yeah.
So the question that came up is why do we do that? Why don't the
Okay.
neural network
Computer.
itself understand what are the important features that it should extract?
Mm-hmm.
So that makes it a completely end-to-end model
Mm.
where we just pass an image,
Okay.
it extracts the key features of that image,
Okay.
and then pass it. They take those key features as an input to our neural network,
Mm-hmm.
pass it to our neural network, calculate it, and finally identify which image it is.
Okay. So instead of we passing HOG and LBP,
Mhm. The
uh,
system itself recognizes that,
the system itself.
recognizes those patterns, but not exactly in the exact algorithmic way that we do.
Mm-hmm.
But it creates its own pattern in recognizing them.
Okay. Okay.
So
Okay.
this, like, which one do you think is like now we have totally three models where
Hmm.
all neurons are treated as pixels.
Mm-hmm.
The second part where the feature extraction is done and it is passed to a neural network.
Mm-hmm.
The third is an end-to-end where like we just pass an image, feature extraction is done automatically by the system, then
Mm-hmm.
passed to a neural network, then like it makes some
Yeah.
output prediction, again loss calculation,
Mm-hmm.
adjustment of weights using back propagation. That
Mm-hmm.
happens multiple times until we get the final output.
Yeah.
So which algorithm do you think is like the most efficient one?
The third one, wherein the machine does all the.
Right, because when we do that, the machine can also learn patterns that we might miss as human beings.
Yes, there are a lot of things we human being can miss, like
They
in
can,
a image. Yeah.
yes, and they tend to see that intricate patterns that are available in that image, and then they extract those features.
Okay.
Okay, so for
Okay.
that, to exactly to do the same task that we are discussing till now, the
Mm-hmm.
end-to-end model, we
Mm-hmm.
are using convolutional neural networks.
Okay. So we actually don't introduce HO, hog and LBP.
No, no, we don't use that. We have that. We can do it in that way as well.
Okay.
It's
Okay.
not like we don't have that algorithms or we
Okay.
cannot
Okay.
do that using that.
Okay.
But convolutional neural networks help them, like, I mean, to remove that step. So why
Okay.
should we do that? We should extract certain features, once again pass them as features. Why should we do that when the neural
Mm-hmm.
networks are capable of doing that?
Okay. Understand.
And that is the reason why neural networks are very, very powerful.
Okay.
Convolutional neural networks are very powerful.
Mm-hmm.
In fact, convolutional neural networks, when applied in a most appropriate way,
Mm-hmm.
they very much help. They are very powerful, and convolutional neural networks are the one that have been, like, I mean, in news every time whenever a Kaggle competition is won on ImageNet.
Okay. Okay. So
So
all these feature recognition, movement of a robot, and all, like wherever the like visualization comes into picture,
mhm.
all these are working on convolutional neural network, is it?
Most of the times it is convolutional neural networks itself.
Okay. Okay.
Okay, the base architecture is always convolutional neural networks.
Okay. Okay.
Okay,
Okay.
so now it is important that we really understand how a convolutional neural network works.
Okay. Yes.
You will have a lot of articles on web on convolutional neural networks,
Mm-hmm.
but if you go through them, I personally I felt that there isn't any article or there isn't any very clear cut explanations on what really is a convolutional neural network
Okay. Okay.
and what they can really do. Like it's like an end to end that can say that, this is a convolutional neural network, this is where it begins, this is where it processes, this is what is the result, and how we can visualize them.
Okay.
There isn't,
Okay.
so there isn't very, like, I mean, good descriptions, and many people still feel
Mm-hmm.
convolutional neural network as a black box.
Okay.
As an
It's the black box of AI.
Yeah, for many people, the reason is
Okay.
because of the very inappropriate kind of explanations that are available,
Okay.
and somebody owe that to be very complex. But to be
Okay.
honest, but to be honest, the maths that is involved in convolutional neural networks
Mm-hmm.
will not create any discomfort to even a sixth or a seventh standard guy. They are
So
that
it's
simple.
that simple.
It is that simple.
Okay.
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 It is
Okay.
just a very, very simple math that is involved. Very
Okay.
simple math
Okay.
that is involved.
Like a
But
multiplication,
it,
division, like
it is
something
just
like that.
about multiplication and addition. That's it. If we are good
Okay.
with that, we are good with convolutional neural net.
Convolutional. Okay.
Yes.
Okay.
So it is a very, very simple algorithm, but it is important to understand how that is structured
Hmm,
and
hmm,
how
hmm.
that helps in really recognizing a feature
See,
map.
major issue I think is coming in picturing that how to format that algorithm,
Exactly.
like how
Exactly.
to architect it.
Exactly.
Yeah,
So
because
visualizing
programming
what
wise, there are only few steps that you have to do.
exactly programming wise, like for example, when we created neural networks,
Hmm.
from the time we create a sequential model till
Hello.
the time you train and fit a particular model,
Hmm.
it hardly takes some 6 to 8 steps of
Hmm.
lines of code, right?
Yeah, that's what I'm saying. The programming
Yeah,
thing is like you can learn five different type of things and then you can apply.
apply it
But
exactly.
major issue comes in your
It is like we're learning what is happening behind the hood.
yeah,
Yeah,
that's very
yeah,
important.
that is very important. So even we see the same across even in convolutional neural networks as well. We
Okay.
try to understand what is happening behind the scenes and understand how convolutional neural networks really extract features. of
Okay.
convolution.
Okay.
We will try to do that today.
Do
Okay.
that today. Okay.
So by the end of this class, you should be very comfortable with understanding what a convolutional neural network is, how
Okay.
convolutional neural networks will be able to extract key features of an image, and how
Okay.
we are able to like maximize the performance, why it maximizes the performance compared to a conventional neural network or a
Okay.
regular
So
neural.
you said that in my CV I should write about facial recognition and all. So
Yes.
that majorly involves convolutional.
Yes, definitely. It is
Okay.
convolutional neural networks.
Okay. Okay. So I
Okay.
have to be very smart with this one.
Yes, and I yeah, and I trust me, like this will be made so simple and easy to understand
Mhm.
that convolutional neural networks will become like you will never think that it is like as difficult as it is perceived outside.
Okay. Okay.
Okay,
Perfect.
so
Perfect.
yeah, so now when you start speaking to any other person who is into deep learning and really understanding about
And this is
convolution,
part of deep learning, is it?
yes, the moment you apply convolutional neural network, it is perceived as a deep learning.
Okay. Okay.
Yes,
Okay.
so this is our first introduction to our deep learning
Deep
sessions as
learning.
well.
Okay.
So convolutional neural networks.
Yes.
So before we once again go into convolutional neural networks, let us take a step back.
Okay.
Okay, let us take a step back and understand what is the architecture of a regular neural network.
Sure. Sure.
Okay, so in a regular neural network, first we have the input layers.
Yes.
Input
Input layers, then the okay.
layer that
Hmm.
is followed by hidden layers, which
Hidden
we call
layers.
them as fully connected layers,
Yeah.
because every hidden layer is connected to all the neurons in its previous layer.
Hmm.
So we are connecting it to a fully connected layer,
Hmm.
and a fully connected layer is now once again followed by an activation,
Activation function.
right?
Yeah.
So though we call activation function, it is generally, though it is considered as a layer again,
Hmm.
but it is in fact not a layer, it is a function that we are going to apply. But the reason we
Yes.
consider it as a layer is because we are going to get different outcomes compared to the previous values. Here we have one different set of values, and altogether here there will be a different set of values. That is
Yes.
the reason activation is also considered as a layer. But even if you go through some real seminar papers of convolutional neural networks and all, some people
Mhm.
tend to exclude these activations. And they just say,
Yeah.
because it is understood that between every two fully connected layers, there is going to be an activation.
Activation for every layer. What we even in the programming what we were doing
Mhm.
every layer we introduce a
An
um,
activation,
activation function.
right? But it is always good to explicitly state an activation
Okay.
rather than like telling, because that is when you can really have the comfort of telling which activation that you have used.
Okay. Okay.
But if we explicitly state it outside, then we, for example, I can include a ReLU, then a tanh, then a ReLU, then a softmax. I can do
Mhm.
that, right?
Okay. Okay.
But if but we are telling explicitly that we are using an activation, we really never come to know what exact activation was used.
Yeah, but we introduce like when we program, we introduce for each layer an activation function, right?
Yes, we introduce an activation, but
Mm-hmm.
most of the times we used only ReLU.
ReLU, yeah.
Most
Mostly
of the
we are
time
using
using
ReLU and
ReLU.
then softmax
Final
for the last
class, yeah, for the final class it is softmax, but we can use a combination of them as well.
one. Okay, okay.
Okay, so
Mm-hmm.
again, this can continue for at least 2 to 3 times based upon the number of fully connected layers that we have,
Mm-hmm.
right? So into n, where n represents the number of times that we repeat this process.
Okay, so you're saying ReLU for all the layers, like into number of layers.
Yeah, or to be more like precise, I'll say an activation.
Okay.
Activation can be anything. Okay,
Mm-hmm.
we can apply whatever the activation we want between the fully collected layers.
Mm-hmm.
um, fc layer. So this follows fully
Okay.
connected layer, activation, fully connected layer, and again an activation. This particular process
Mm-hmm.
loop goes on for multiple times.
Mm-hmm.
So activation is followed by again a fully connected layer. So this happens, and once like we do it some like 2 times or 3 times, we do not do even much more. We do not add some 20 layers or 10 layers, right?
Okay, yeah.
Generally two
Four to
three
five,
layers,
three to
yeah,
five
like
is what
sufficient,
we
more than
yeah,
sufficient enough.
yeah,
So then when we do that, the final layer of
mm-hmm.
this will be a fully connected layer. Okay,
Yeah.
then there we are
Which
going
is
to
which
softmax.
is the outcome it seems.
No, the fully connected layer is now okay. Even if you consider that, like I want to specifically
Mhm.
explicitly say softmax, because here whatever the activation
Okay,
can be
okay.
used, here it is only a softmax.
Mm-hmm.
And whatever is the, once we apply a softmax, Whatever the result we get is an output layer
Okay. Okay.
after applying softmax, right? So this can
Yeah,
be
after applying the software, you get the output.
the result
Yes.
is the output. So this can be considered as the regular architecture for any general neural network.
Okay.
This is what we have done till now as well.
Yeah. Till now, neural networks is exactly
Exactly
this
the
is
same.
yeah.
So any questions on this? Is it clear?
It's pretty clear. Yeah.
Yeah. So now here, once we do this neural network, so now when we are telling something like a bit advanced to this, if I want to make it as like something like an advanced neural networks, okay. Okay. Here I do something else.
Okay.
What I do is I say input layer, okay, feature extraction,
Okay.
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 Now fully connected layer, activation, that is multiplied n number of times. Then fully connected layer, that is softmax, and now output layer.
Okay. So the difference, what I see here is before fully connected layer, we have introduced a feature extraction.
So the output of feature extraction is an input to our fully connected layer, right?
Yeah.
So this is a bit more advanced, and this feature extraction is done by using like different classifiers that we discussed.
HOG or
LBPs, etc.,
LBV.
etc.
Yeah.
These are done using
So the
this
only difference here I see is the introduction of feature extraction after the input layer.
Yes, the reason this feature extraction is important is because we know that all the features in that particular image need not be really necessary to really depict an entire image. All the neurons may not be really important. So that is the reason why we are using such kind of feature extractors. Okay, these are a bit advanced layers, but now we want to automate this part.
Yeah,
We want to automate
this is the crucial difference, and this is the most crucial
thing, which extracts the key important features, right? So we want to automate this part that is highlighted in green, and that is the reason why we use convolutional neural networks.
Okay. So this is all. This is the major feature. This is what's the difference between convolutional and a neural network.
Yes. And when we use convolutional neural networks, one more advantage that we get is something called as dimensionality reduction. So in an earlier image, like let us say 28 by 28 image, we have a total of 784 pixels.
Yes.
784 pixels.
28 by 28, 784. Yeah.
784. But maybe once the feature extraction is done, we might decide that all the 784 pixels may not be very important. Instead of that, this can be reduced to a lower number. Okay, because only that particular features that help us determine what is that particular letter, maybe those edges,
Yeah,
or the corners, and then the entire feature itself.
maybe the surrounding ones. Yeah, nearby ones.
Exactly. They are like extracted using this. Okay. That is what is done in using convolutional neural networks. It is going to detect these particular edges, and so our input layer. So once the feature extraction is done, this feature that particular vector is no more a vector of 784. So is no more a 784 pixels value.
Yeah, it's reduced to only the important ones.
So hence this reduces the number of parameters that we pass to our neural network. So the training is much more efficient because it is taking only those that matter. And at the same time, it is also like easy because the number of parameters that we are using to train has become less.
Yeah.
Okay. So, but if you see a very small image like an MNIST database, we can see that the time taken to execute a convolutional neural network is comparatively higher than our regular neural network.
Yeah, because of this introduction of the feature extraction.
But if we take some really big images, then the number of features that are in that in a regular neural network will be very, very high.
Yeah.
right? So at that time, neural networks not only tend to perform slow, but at the same time, the accuracy will not be very good. But when we introduce convolutional neural networks, this feature extraction, though it takes some time, we are okay, because at the end of the day, that is helping in improving our accuracy, which we are going
Accuracy.
to see.
Okay. Okay.
Okay. So,
Okay.
so this is about
So
convolutional.
this, I'll just make a note. So after
Mhm.
input layer, we introduce, we introduce
I will tell you that I'm still
feature
going to
extraction.
form.
Okay.
I'm
Okay.
still going
Okay.
to
Okay.
form
Yeah.
that
Okay.
convolution.
Okay.
So
Okay.
now in neural networks, how is this future extraction going to happen? That is
We
all. Mhm.
as machine itself forms a like trains itself to do the
To do
feature
the feature
extraction.
extraction. But
And
for
there
that,
are other ways also like HOG and LBP where
yeah,
we can also do it
yeah, we
faster.
provide those particular algorithms. Okay.
Algorithms as per the picture.
Yes.
Mm.
But when we are using a convolutional neural network, let
Mhm.
us take the common architecture of a convolutional neural network. Now, since we understood like how neural networks and a bit advanced neural networks work,
Mhm, mhm,
now let us really see how convolutional neural networks work. So in a convolutional neural network,
mhm.
the first layer is definitely an input layer.
Yes,
Now,
just like a neural network.
just like a neural network,
Mm.
that is
So
followed.
these are
Yeah.
all like in neural networks, the neurons, the number of neurons were the features. In here also, it is the same, right?
Yes, yes, yes. Neurons
Mhm.
are the features. Even here, the neurons are the features. Each neuron holds certain pixel value,
Okay.
right? Even that is common across even in a neural network,
In
even in a
neural network.
convolutional neural
Okay,
network as well.
perfect.
But even here, we do not take all the neurons, but we take, oh, sorry, all the pixels, but we take only those pixels
Okay, okay.
that are important to us.
Important.
Yeah, only that pixel will form our input layer. So every feature in our, every neuron in our input layer contains a
Mhm.
pixel value.
Okay, okay.
Okay, is it clear?
Yeah.
So the first layer is always the input layer. When I
Mm.
say input layer, we can consider this as our image,
Image.
not
Yeah.
our first layer of our neural
Yeah.
network, fully
So it
connected neural
usually
network.
will be features would be 784 features
But yes, so in this case, you can think that 784 is the image. Okay, so first
image.
thing we do is we pass the image,
Yeah.
the entire image.
Hmm. Hmm.
So the input is always an entire image. Okay,
Yeah. Yeah.
once we
First thing is entire image. Yes.
entire image. So once we do this,
Mm.
then it is followed by a convolutional layer. We see what happens in a convolutional layer. Okay,
Okay.
we'll
Hmm.
see what it is. So at least at this
Okay.
time, understand that first layer that we are going to pass is not that hog or LBP feature extraction,
Hmm.
nor it is a fully connected layer, which is a hidden layer.
Okay.
There is a special layer called as a convolutional layer. Okay,
Mm.
this convolutional layer is followed by an activation layer.
Okay.
Okay,
Mm.
and this activation layer is followed by a pooling layer.
Pooling. Okay.
Pooling layer, and this generally repeats for like at least couple of times.
Okay. Okay.
At least couple of times we repeat this.
Hmm.
Okay,
Mm.
no definite standard that you say that you have to run it 2 times or you have to run it 3 times or you have
Okay.
to run it 1 time. Based upon your architecture, the accuracy varies. And that is the
Hmm.
beauty of how we think and we decide our architecture and we put it to practice.
Okay.
Because these are certain things that really affect our accuracy. And these are the things that are really going to put above and below our leader tables whenever we are working on some very high level projects like ImageNet projects,
Okay. Okay.
our research. Okay.
Hmm.
So now, once we get this convolutional layer followed by an activation, followed by a pooling, this happens like a couple of times.
Hmm.
Then the final result, then whatever the result we get, that will be
Hmm.
flattened. Flattening is not a pooling, okay?
Okay.
Like it is just an operation to bring that everything into a single array,
Okay.
okay, of numbers. Then that will be followed by a fully connected layer. Okay, hello.
Yeah. I'm
Yeah,
listening. Yeah.
fully connected layer is nothing but a hidden layer. You can treat it as a hidden layer, okay?
Okay. Okay.
But
Okay.
now the
This is the
input,
first hidden layer. Now this
yes,
here comes the first hidden layer.
hidden layer. But the input to the hidden layer is the output of our pooling. By the
Pooling.
time we
Okay.
complete the pooling and all, and we get certain pixels, that is
Mhm.
the input to our
So
first.
convolutional network, which is active, then followed by activation, followed by pooling into
Mhm.
n number of times.
Yeah, we repeat
This
that
is
again and again.
this is what we were calling about. as feature extraction.
Yes, yes.
Okay,
So
okay,
by the
okay.
time we do convolutional layer, we pass through a convolutional layer, complete like activation,
Mm-hmm.
and then once again we do the pooling, and we do
Okay,
it couple of times, or like even we can do even once, couple of times, and so on. When we are
okay,
doing that, we are doing the feature extraction process,
okay, okay, okay.
and then it is connected to a fully connected layer. Once it is connected to a fully connected layer, then we do something called dropout. Drop,
Dropout.
yeah,
Okay,
dropout is generally used for dealing with generalization problem that we discussed yesterday. It can
okay,
go with training and testing, but may not go really with the real-time data. That is where
okay,
dropout
okay.
helps. We'll see what dropout is.
Mm-hmm.
Okay, and then once again, it is fully. It is, um, yeah, we do a dropout,
Mm-hmm.
and then
So
a
what?
fully connected
Okay.
layer.
Mm-hmm.
Sorry, a fully connected layer is once again generally passed through an activation again,
Okay.
and then it goes through a dropout
Mm-hmm.
again. Like I mean, the result once again will go to a fully connected layer, and typically we can repeat this
Mm-hmm.
process if required. You can repeat this process like a couple of times. It depends upon you.
Again.
If you want,
Okay.
yeah, if you want, you can do it here, or you
Mm-hmm.
can do it here as well. It depends upon you
Okay. Okay.
how you want to do. Okay,
Mm.
you repeat this process couple of times. So I'm mentioning it as some yum based
Mm-hmm.
upon how many number of input layers you need. Sorry, full hidden layers you need.
Mm.
Okay, once we repeat this process, the
Mm-hmm.
final output will be once again a fully connected layer. Okay, but here
Mm.
this time we are going to use softmax,
Okay. Okay.
and the output will be,
Mm.
and the output is going to be output layer. Vikram, just give me a minute. 1 minute,
Hello.
please.
Yeah. Take your time. Take your time.
Yeah. So
Yeah.
thanks. So
No. No problem.
yeah. So once this is connected to fully connected layer, that is when we get an output. Okay. This is
Okay.
finally this is called as an output layer.
Okay.
Okay. So so like leaving convolution and pooling and a dropout. Is there any question regarding any of the other layers? It is just still the same. Our input, which is our entire
Mm-hmm.
image. Hello?
Hello.
Yeah. Can you hear me? No?
See. See. I'll explain understood. Hello.
Yes, yes. Just a minute. Just one.
Hello.
Ah, yeah. Now it should be
Yeah.
clear.
No. Yeah. Clear.
Yeah.
Okay. So what I've understood is, so first is the input layer as we put it in the neural network.
Yeah. It is a regular image, entire
It's a
image.
regular image, the entire image, like 28 by 28
28.
pixel.
Yes.
Yeah. Then we take it through a convolutional layer. You said.
Yes.
Okay. After this is where we feature extraction. Like this is where we start our
Feature
convolutional network.
extraction.
Yeah,
Yeah.
feature extraction.
Yeah.
Now in this whole feature extraction, now we start the next part is the activation function which we introduce,
Yes.
and this can be and this whole okay. Anyways, activation and then pooling. Pooling is something which I've never heard of. We'll discuss about it.
We'll
Pooling
discuss. Yeah.
So this whole thing into n is the
This whole
extraction
process is repeated multiple times.
multiple times,
Yeah.
and this whole process repeated multiple times is HOG or LBP.
No, we are not using any HOG or LBP because the
Okay. Oh,
concept of
it's the feature extraction. Sorry,
yeah, because
those
yeah,
are particular algorithms
yeah, they're hand
which they
engineered
do
algorithms, but these are automatically taken care by our neural network itself.
neural networks. Okay. So basically, feature extraction is happening here,
Yes, yes,
wherein the machine extracts the important features which help identify the image exactly.
yes, yes,
Yes. Then this one goes to the first connected layer,
yes. That is a
right?
hidden layer.
The first hidden layer in
Yeah,
neural,
FC refers to fully connected layer.
fully connected hidden layer. Okay.
Yes.
Then we pass it through an activation function,
Hmm.
and then DO was
The dropout.
dropout. This we will discuss.
Yeah, we'll
Dropout, I don't know.
discuss. Yes.
And then this also is repeated.
Yeah. Based upon our wish, it
And
is repeated multiple times. It can be once or twice.
okay, so
We
this
can do that.
FC is only the first hidden layer, right?
Yeah.
Or all the
Like
hidden layer?
yeah, FC means fully connected layer. It can be the first, second, third,
Oh,
any
it
kind of
can be
hidden.
any.
Yeah.
Okay, okay.
So
And
we do
then
that again, and finally, once again, we have a fully connected layer at the end.
at the end,
That
through
is
which we pass that layer through an activation function softmax,
yeah,
which gives us the final output.
final output layer. Okay. So
Perfect.
now, yeah. So now, the only three things that we have to understand in the whole process is what is a
Mm-hmm.
convolution,
Mm-hmm.
what is pooling, and what is
Mm-hmm.
dropout.
Yes.
If you understand these three, I guess like we are done with convolutional neural networks, right?
Okay.
Because we know the architecture so well now.
Yeah.
Let us understand
So
what
convolutional pooling and dropout.
yes. So let
Yeah.
us come with dropout first.
Mm-hmm.
Okay.
Mm-hmm.
Dropout is something that we like. I mean, that it's a simple thing. It's
Mm-hmm.
very not too complicated at all. Let
Okay.
us imagine that I have a 3 bar 3.
Okay.
Okay, this is one. Let us say this is one hidden layer.
Mm-hmm.
This is the other hidden layer. Okay.
Mm.
In reality, these hidden layers need not have the actual same values. Like
Yeah,
three
it
and two,
can be
you can
different.
have
Yeah.
3 and 2 as well. 2 and 4. It can be anything. Okay.
Mm-hmm. Mm-hmm.
So now the connections will be like this.
Yeah, all are connected to each other, fully
Each
connected.
other. Yes. This is how is a regular neural network.
Mm.
Now, during a process of dropout, what we do is we randomly remove certain connections
Okay, okay.
like this.
So we do it or is the machine doing it?
When we provide what is the amount of like I mean connections to be removed, 10 percentage, 20 percentage, we
Okay,
pass it as a
okay,
parameter and say remove
okay,
so many connections.
okay.
So the system automatically and it does it randomly. It doesn't say that only this has to be removed and this has to be removed. It doesn't say
Mhm.
that. It
Okay,
randomly removes certain connections.
perfect.
So that the system need not depend upon all these in order to get. Even
Mhm.
if certain connections are removed, still during the process of training, it can still learn the features from the other values.
Okay.
So that is when it can generalize it to a generic community outside.
Mhm.
Otherwise, it depends upon exact values of these particular neurons itself. Only based upon the values of these neurons itself, it
Mhm.
gives a final extraction.
Okay.
As a dropout, we are since removing certain connections, still it will be able to generalize based upon the only existing values. Still, it can find out what is the best fit,
Okay.
what is
So
the best
dropout
class.
is basically randomly dropping the
Certain
connection,
connections in certain few connections in the neural network.
dropping few connections in neural networks. Okay.
Okay, so
Mhm.
this process is called as dropout,
Okay. Okay.
randomly removing
So
certain
why
connections.
is this taking? Why do we do that? This?
Because we do that to counter generalization and overfitting. At times, only this exact pattern is to be matched in order to get the final output, like to determine it's a cat. But now,
Okay.
when
Okay.
we randomly remove certain connections, still
Mhm.
our network learns that it is a cat, even though we do not have certain connections.
Okay. Okay.
That helps in generalizing cats and dogs
Okay.
or
Okay.
whatever the features it is.
Okay. Okay.
It is
Okay.
used for generalization and to prevent overfitting.
Hello.
Hello, can you hear me?
Yeah. Yeah, I can hear
It
you.
helps to prevent overfitting and helps in generalization.
Okay. Helps in Helps.
preventing overfitting, and in generalization.
Okay. Yeah.
Okay. Okay.
Hmm.
So any questions on this? Is it clear?
No. No. Yeah.
So now one part of it is done, one black box is done. So still we
Hmm.
have two more, convolutional and pooling.
Yeah.
So in order to explain that, I took some time to prepare one Excel. Okay.
Oh. Okay. Okay.
Yeah, because that definitely makes it a lot easier to understand completely
Hmm.
this neural
Okay.
networks.
Okay.
So let me, okay.
Hmm.
So are you able to see the screen?
Yes.
Imagine I have an image of pixels 5 bar 5,
Yeah. It's 5FR. Yeah.
5 by 5. So I have 5 pixels in height and 5 pixels in width.
Hmm.
Okay. So now,
Yeah.
since we have this image, I want to apply a convolutional layer onto this image,
Okay. Okay.
because our first part is now we are discussing what is a convolutional layer here.
Hmm.
First thing, we are trying to find out this part, convolutional layer, what a convolutional layer is.
Yeah.
First thing is we are taking an entire image and passing it to our convolutional layer, right?
Hmm.
So I took an entire image, which is a 5 by 5 pixel image, 5 pixels in
Hmm.
height and 5 pixels in width. I've taken this image. I should pass this through a convolutional layer. Okay.
Okay. Okay.
So if I do this,
So this basically you're talking about, like, if in case it's an image which usually is 28 by 28, we are taking it as 5 by 5.
so let us think, yeah, generally we have 28 bar, but in an Excel, I cannot represent 28 bar
Yeah,
in
yeah,
an
that's
Excel.
what, to make it easy. Yeah.
Yeah, to make it easy, I just took a very small image of 5 pixels in height and 5 pixels in width
Mm,
instead of any 28 bar 28 and all.
mm, mm,
So a small image. Now I take one matrix called as a kernel filter. Okay,
okay.
called as a kernel filter. What
Mhm.
this kernel filter is initiated with some random values.
Okay. Okay.
Okay, but there
Zero,
are,
one, and minus. Okay. Some
yeah,
values.
yeah,
Okay.
but there is a principle to that, that
Mm,
these values should always be zero centered, which means I take an average of this,
mhm.
it will count to zero.
Okay. Okay. Yeah. Yeah. Yeah.
That's how we
Yeah.
generally take. That is a
Yeah.
good way of initializing random values. Even in
Mhm.
our neural networks, when we initiate a kernel, generally we do not do that. We do not give that parameter. But by
Mhm.
default, it uses a Glorot uniform parameter initializer. Sorry.
Okay.
So that is a technique of initializing the random bits. It's not like they are completely random. They are structured in a way. Though the number is random,
Mhm.
it is still they are structured in such a way that they are always zero centered. The mean of them tends towards zero,
Yeah.
because it is proven that they such kind of random values will have more impact than the others. That's when learning can become much more easier. Okay, so
Mhm.
we initialize them, and there are certain filters, like for example, if you see a filter like a Laplacian filter, this kernel matrix has a very standard numbers. For
Okay.
example, if you want to apply a blurring operation on this image, if you
Okay.
want to sharpen that image, we have
Mhm.
different predefined kernels already available. So if
Okay.
you use a definite pre-variety of predefined kernel, you will be able to sharpen that image.
Okay.
In whenever we open an image in
Mhm.
our gallery, we will have different options, right? Like
Yes.
sharpening
Yes.
the
Yes. So
image, blurring
sharpening.
it.
Yeah.
Yeah,
Yeah.
that kind. So for every kind of one operation, there is a specific predefined filter. Okay.
Okay.
So but here in this case, like if we want to perform that operation, we take a predefined kernel. But here
Mhm.
we are just taking one random kernel with some random bits. Imagine at this point of time, it's just a
Mhm.
3 bar 3 pixel,
Mhm.
three pixels in height and 3 pixels in width kernel. Okay,
Mhm.
the general size of a kernel is always 3 bar 3 or a 5 bar 5.
Okay. Yeah.
Okay, but
Mhm.
what did this kernel do? It is just a random like I mean a matrix with,
Mhm.
when I say, because these are all represented in terms of matrices, right? Like in terms of rows and
Mhm.
columns.
Yeah.
So this is a random matrix of 3 bar 3, three columns in width and 3 columns in height.
Mhm. Mhm.
Sorry, yeah, 3 columns in height and 3 columns in width. So
Yeah.
it's a 3 bar 3. What I do is I first place this kernel. I plus
Okay.
so let me switch on my video,
Okay.
uh, because sometimes if I do certain kind of facial
Yeah.
expressions,
Yeah.
that is
Yeah.
something that is important. So like on my side, the latest thing
Mhm.
that there is a 5 bar 5 image. Okay,
Okay.
and
Mhm.
here there is this 3 bar 3 pixel image.
Okay.
First,
Okay.
what I do is I place this 3 bar 3 pixel image onto my 5 bar 5 image. Okay,
Okay. Okay.
I place
Okay.
it like this. So I
Mm-hmm.
place this. Now you can see the screen again. I place
Yeah.
this 3 bar 3 pixels here.
Mm-hmm. On
I
top
place
of
them
5 by 5.
exactly on this 5 by 5. So they exactly overlap like this,
Okay. Okay.
right? When I
Mm-hmm.
overlap, what I do is I do an element wise multiplication of these numbers, which means I
Okay.
multiply 95 with minus 1.
Mm-hmm.
I
Mm-hmm.
multiply 242 with 0.
Mm-hmm.
I multiply 186 with 1. Okay.
Okay.
And I multiply 39 with minus 2, 14 with 0,
Mm-hmm.
220 into 2.
Okay.
Again 5 with minus 1,
So the
247
three
into
by
0
three, the first 3 by 3 of this image by 3 by 3 of the kernel.
of this image. And it is not
Mm-hmm.
a matrix multiplication like I do 95
Yeah,
into
yeah,
minus 1.
not that.
Not
Yeah,
in
it's
that
a
way.
straight
It's just
multiplication.
a straightforward element wise multiplication.
Yeah, yeah.
The first element multiplied with this, the second element multiplied with this, the third element multiplied with this.
Mm-hmm.
Similar way for the entire 3 bar 3. So for the entire stuff,
Mm-hmm.
okay, I multiply them
Mm-hmm.
with these values. Okay.
Mm-hmm.
So every element, these two are multiplied with the same values. Like I can say, something like this. These two are multiplied with again a similar values, and these two are multiplied with the same values.
Yeah.
I think this
Yeah.
is much clearer.
Yeah, this is, yeah, yeah.
Yeah.
No, I understood what you're saying. Like
And
95
similarly,
with minus 1, 242 with 0, 186 with 1.
yeah.
Then in the
Similarly,
second row,
39 with
39
minus
with
2,
minus 2, 14 with 0, 220 with
220 with 2, and again 5 with minus 1,
5 with
247 with
minus 2,
yeah,
0, and 200.
212 with 1. Okay, and
Okay.
I just add all these. I just add them. So
Okay.
95 into 0 into minus 1 is minus 95
Mm-hmm.
plus 0 plus 186 plus 39 into minus 2 plus 14 into 0 plus 220 into 2 plus minus 5 plus 0 plus 212. So I add all these elements, I get one single number.
Okay.
Okay, so for example, if I multiply this element wise operation, so
Mm-hmm.
like if I do this, for example, it is like 95
Mm-hmm.
into 1 plus 242 into 0 plus 186 into 1 plus 39 into minus 2 plus 14 into 0
Mm-hmm.
plus 220 into 2. Okay,
Mm-hmm.
plus sorry 5 into minus 1
Minus 1, 247
plus
into 0,
yeah 247
212
into 0
into 1.
plus 212 into 1.
Mm-hmm.
Okay, the value is 660.
Okay. Okay.
Okay, so this is the first value that I'm storing it. Let us say I'm storing it here. Okay,
Mm-hmm.
now what I do is I just move this selection. So now like earlier this is our selection, right? Now I move the selection one step right. So earlier I applied this kernel onto the first three images.
Then the second,
Now I
third, and
apply on the second, third, and fourth.
fourth
So
column.
this becomes this, and this becomes a white. So now
Okay.
the kernel is applied on this.
Mm-hmm.
And we again perform the exact same
Same.
operation that we 242 into minus 1 plus
Mm-hmm.
186 into 0 plus 152 into 1 plus 14 into minus 2 plus 220 into 0 plus 153 into 2
Mm-hmm.
plus 247 into minus 1 plus 212 into 0 plus 54 into 1. We get some value that is
Mm-hmm.
placed here.
Okay. Okay. And then
And
again we do with.
we once again do with the last three. So
Okay.
we eliminate this
Mm-hmm.
and we apply on this. Okay.
Mm-hmm.
And then we come to this part. Once we are done with this,
Okay.
once we're done with this, we come to these three.
Okay. Then lower. Okay.
Yeah, we
Okay.
just
And then.
come one step down. So we eliminate, we skip all this time we are skipping the first columns, right?
Mm-hmm.
And
Mm-hmm.
moving
Our
one step
rows.
right. Now we are skipping one row. So we come here. So these
Mm-hmm.
three form this, the last three form this.
Okay. Okay.
So now by the end of this operation, we get a 3 by 3 column matrix,
Mm-hmm. Mm-hmm.
right? So
Mm-hmm.
that matrix, if you see, for example, is this one. Okay.
Mm-hmm.
So this is, so first these three multiplied this will give 660.
Mm-hmm.
These three multiplied by these three once again give minus 5.
Yeah.
The last three multiplied these by these three give
Minus
minus
390.
393.
Mm-hmm.
Again these three
Mm-hmm.
multiplied by this kernel gives 682.
Mm-hmm.
This 3 multiplied by this kernel gets 214,
Mm-hmm.
minus 214. And the last 3 multiplied by this kernel gives minus 431. And finally, the last row
Mm-hmm.
multiplied by this kernel gives 299. This 3 with this 3 gives minus 69. And these 3 with this kernel filter gives minus 242. Okay.
Mm-hmm.
Now, like here, we are moving always, we are skipping one column or one row at a time, right?
Mm-hmm.
Then skipping that by one row or one column is called as a stride. By how many units are we moving?
It's called trade.
Stride. STRAD,
Right.
stride.
Okay.
Okay,
Right.
it's represented by a thing
Yeah.
called
Yeah.
stride. We can, for example, in the same thing, for example, if I take a 3 bar 3, I get a value 660.
Mm-hmm.
I need not skip one, but I skip two and I come here directly,
Okay. Okay.
right? So I skip in between one and directly come to the other. So in this way, if I do, it is
Mm-hmm.
called as a 2 stride.
Okay. Okay. Okay.
Okay. So if from here I'm directly coming to the next is a 1 stride.
Mm-hmm.
If I'm directly coming to this part, it is called 2 stride. Okay.
Okay.
If I take a 2 stride, what will be my final feature map? For example, if I take 1 stride, it is a 3 bar 3. The outcome is a 3 bar 3, right?
Mm-hmm.
If I take a 2 stride, what do you think will be my feature map? What will be my final outcome? Will it be again a 3 bar 3?
Which one?
If, for example,
Mhm.
if I'm taking this 5 by 5, 5
No,
by
it
5.
won't be 3 by 3. If we skip two, so
So
if we
this
skip
will
two,
give
it's two
1.
by two.
Exactly.
It
Perfect.
will be
It will be 2
two
bar
by
2
two.
because this is 1, this
Yeah.
is 1,
If we
2,
skip two, yeah.
and here this is the third, and this is the fourth.
Fourth.
So it's a 2 bar 2 stride. Okay. So now I'm,
Right. I'll make a note. Yeah.
yeah. So, so now if you do
How
this,
do
if
we
you do
choose?
this with
How do we choose like
the
we,
strides,
yeah.
the default stride is 1. Okay.
Okay.
But we can, it is like more like an experiment that we do with the 2 stride as well, more than one. We do a first stride and a 2 strides and we see the performance.
So
It's not
do we
always,
do this or it happens behind the scene?
no,
Like
we have to
we
give
just pass
stride as a parameter.
parameter. Okay.
Yes.
We have to
But
pass
again,
it as a parameter and it
yes.
happens.
Yes. And
Okay.
passing a stride is not a mandatory parameter, which means if you don't pass it as a parameter, by default, it will be taken as 1 stride.
Okay. Okay.
Okay. And you can also tell the strides in like the, what I can say, row wise and column wise skip. Like you can say like 1 stride in the row wise and 2 strides in column wise,
Okay. Okay.
which means in row
So
wise
we
I
can
get,
alter the like column wise we can have two and row wise we can have three,
have
like two by
3.
three.
Yes, we can have, but generally we prefer an even number of strides
Okay. Either two
because
by two, three by three, like that.
yes, like that, because that gives us, that helps us to efficiently optimize our linear algebra programs that most of the times use square matrices.
Okay.
Okay, so generally it is
Yeah.
preferred to have such kind of strides in like, I mean, 2 by 2 or 3 by 3 like that. And we rarely use any strides that are greater than 3 by 3.
We don't
Preferred,
use.
yeah,
That's the
preferred is
maximum.
1 by 1, one stride or 2 strides is preferred.
Okay. Okay.
The reason why we do that is because, you
Mm-hmm.
see, ultimately we have to understand that these feature maps are only going to be our output, okay, which is going
Okay.
to be our input for our fully connected layers.
Mm-hmm.
Okay,
Mm-hmm.
so now you see a 5 bar 5 image which has 25 pixels, right?
Yeah.
By the time we applied a 2 stride is reduced to 4 pixels,
Two by two, 4 pixels. Yeah.
right? 4 pixels. So if we apply 2 stride, 25 pixels have reduced to 4 pixels. So what happens is the number of features that we finally get for our fully connected layer, the
Mm.
features for our fully connected layer will drastically reduce. Okay.
Okay.
So
Yeah. From
learning cannot,
25 to
yeah.
4.
So it's like we are giving very few inputs so that the learning cannot be very well.
Okay.
So
Okay.
using very
So
high strides, yeah.
when we use an image, it's usually 28 by 28.
Mhm.
So in that case, what matrices, like what kernel filter do we like? What's the size
We,
of the kernel
the
filter?
basic kernel filter will be 3 bar 3. Stride is
Okay.
1.
Okay.
Okay,
Okay.
still it is a 3 by 3. Kernel size can be, if the images are of higher resolution, we go for a 5 by 5 kernel.
Okay.
Kernel, when I say this, kernel, okay,
Yeah.
5 by 5
Kernel
kernel.
filter.
Yeah, but strides are generally 1 or maximum 2. That's it, nothing else.
Okay.
Maximum 2,
So
but
the kernel filter, in case of 28 by 28, can be 5 by 5,
or a
but
3
the
bar 3.
stride will
Yeah,
be maximum 1 or maximum 2.
yes, that's it.
Okay. Okay.
Okay, so now
Mm.
once we are done with this kernel filter, so are you convenient till now? Is there
Yeah.
any
Yeah.
confusion or
No, no, no. I'm getting there.
right? So now
Yeah.
once we get this strides, okay, which
Mm.
is called as a feature map, generally we do not apply a single kernel. Okay, in reality we
Mhm.
apply multiple kernels with multiple random weights, because that is how the learning happens, right?
Okay.
We let's say, like for the same 5 by 5, I can
Mm.
take 32 filters, 32 kernels.
32.
Okay,
Okay. Mhm.
I can take 32 kernels. Each kernel is of the size 3 bar 3, randomly initiated. So it gives like 32 3 bar 3s with its one stride.
I'm not getting this one. What you said?
For example,
If, yeah.
there is one kernel
Mhm.
gives one feature map, right?
Yeah.
If
So,
I take 32 kernels like this,
okay, okay.
applied on
Of
this,
the same size, 3 by 3. Okay, okay,
the
okay.
same size 3 by 3, okay?
Okay.
So, but the random weights are different. Here it is -1, -2, -1, 0, 0, 0, 1 to 1.
Mhm.
The
Mhm.
second
Mhm.
kernel can be of a different numbers
Yeah, yeah.
initiation.
Randomly generated. Yeah.
Yes. So now once again we do this operation. So this first feature map contains
Mhm.
these values. Second feature map contains a different values. Third feature map contains a different values, right?
Okay. Yeah.
So
Yeah.
now we'll have 32 like feature maps.
Feature maps.
So the number of feature maps depend upon the number of kernels we are initiating.
Okay. Perfect.
Okay.
Yeah.
But the
Mm.
way of calculation remains the same.
Okay.
Okay.
Mm.
Now,
Introducing strides.
yes. Once we do this,
Mhm.
once we do this,
Mhm.
after a convolutional layer, what is the next layer?
Activation.
Activation. So let us go
Mhm.
ahead and apply an activation to this.
Yeah.
So in this again, I am going to apply a Rayleigh activation. Okay.
Okay.
So when I apply a Rayleigh activation, what does a Rayleigh activation say? A Rayleigh activation says that for, okay, if this is the value,
Mhm.
Rayleigh activation takes the maximum of 0 of the number.
Yeah.
This is what is Rayleigh. So I just copy paste this.
Mhm.
Okay. This is the final output activation. Wherever
After
there is -5s, negative numbers, they are converted to zeros,
zeros.
and the positive
Because it's
numbers are like red
because
triangle.
it's been 0 and infinity.
Yes. So
Mhm.
like the positive numbers remain as it is, the negative numbers turn to zeros. So that is the activation layer. You can see
Mhm.
this here. So if I unhide this, so this is how our Rayleigh activation is.
Okay. Okay.
Okay. So
Mhm.
this convolutional layer is passed through an activation layer, and this is what we get.
Okay.
Okay. Is there any
Mhm.
question on this so far?
No. So,
Next.
like supposedly, as you said, we introduced 32 kernels.
Mhm.
So all these kernels would be passed through Relu,
This
right?
Railus. Yes, yes, yes.
Okay.
All the kernels will be passed through Railus.
Okay. Okay.
Okay. You can consider that as
Like
an
for kernel,
array now.
we do strides.
Mhm.
Yeah.
You can
Continue.
consider that 32 as an array. Each array
Array,
contains like 3 bar 3 matrices.
3 by 3 matrices. Okay.
Okay.
Mm.
Now all of them are passed through a relay activation map, and we get this. So we'll get 32 feature maps with these
Mhm.
values.
Okay. Okay.
Okay. Now,
Mhm.
once we do this, the next
Mhm.
part is after activation. What is the next part? Pooling.
Pooling.
Pooling is very, very similar to convolutional layer. Okay. Very similar to convolutional layer, but the only difference between this is in a
Mhm.
pooling layer,
Mhm.
we do not initialize random values for a kernel.
Okay.
Okay.
Predefined, is it?
Yeah, no, not even a predefined. Let us consider it as an empty space, okay, which
Okay.
accepts some values. It is like this, an empty one.
Okay.
It says I can accept any value.
Okay. Okay.
Okay, it is as simple as that. It says like
Mhm.
I'm empty, I can accept any values. It is just a blank one. So what does this blank thing can do to us? So let us go back to this.
Okay.
So it goes, so we have to define like how we define a kernel size. You have to define a pool size as well.
Mhm.
Kernel size, I have defined it as 3 bar 3, right?
3 by 3.
Similarly, I'm defining a pool size. The common standard pool size is 2 bar 2.
Okay. Okay.
Okay, that's a common standard size, which works pretty well in most of the scenarios. Okay.
2 by 2.
Yeah. And stride is 1.
Stride is 1.
Yeah.
Okay.
It's not mandatory again, but as you said, it is a common practice to use a 1 stride and a 2 bar 2 for a pool size. Okay.
Okay.
If you want, you can experiment it with various kinds of activations, various kinds of pool size, various kinds of like, strides, etc., in the entire kernels, etc.
See the
You can do
outcome.
that.
Mm-hmm.
Yeah, that definitely has an impact on the outcome, right? But it
Okay.
depends upon you. Okay. But
Okay.
now a common practice is a pool size of 2 bar 2 and a stride size of 1.
Okay.
Now, as of now, this will be empty because the pool size is 2 bar 2, right? So we have totally 4 values, a 2 bar 2 matrix,
Okay.
two rows and 2 columns. Okay.
Mm.
Now what it does is, since it is empty, okay, place it exactly on top of this.
Yeah.
Okay. So on top of this we place, and out of all these 4, we take
Mm.
only the maximum pixel.
682.
So that will be 682.
Okay.
Okay.
It will be on the top, or it will be at exactly at the same position.
The top, the first part will go to the top part.
Okay. Okay.
The
Okay.
second part will come here. The third will come
No,
here.
no, no.
Fourth will.
Like the pool layer which we introduced on activation Rayleigh. So
Mm-hmm.
660 0, 682 0. This portion.
Mm-hmm. Yes, yes, on this position.
So we choose the highest of all those 4, which
Four.
is 682. So it
Yes.
should be on top, like under that you have written 682 on top of it. Should it be at the top or at the bottom?
Not here. It will be here
Okay.
because
Okay.
this is the first value that we are taking, right? So it will be the first value.
Okay. Okay. Okay.
And then we just, since the stride is 1, we consider these 2.
Okay.
Okay.
Mm-hmm. That is 0.
Yeah. So
Mm-hmm.
now, so now, what happened to this? So now we are considering these 2, right?
Mm-hmm.
1 second. Sorry. Now, since we are considering these 2, the second value here will become a 0.
Mm-hmm.
Now we are considering the max of these 3.
Yeah.
What do you think
682.
is the maximum of these 3?
682.
682. So 682 will be here. You can see a symmetry in which we are updating. It's not
Yeah.
like randomly we are updating. The
Yeah.
fourth one will be for these 3.
Again 0.
Okay.
Mm-hmm.
So the output of the pool layer is 682 0, 682 0.
Mm-hmm.
So once again, this is multiplied again. So now this forms the input for once again our kernel filter. Okay.
Okay. Mm.
But since like it's a 5 bar 5 image, it's a 2 bar 2 pool, it is like so small.
Yeah.
But if you see a very big image, like I mean, for example, if it is a bigger image,
Mm-hmm.
pooling layer also will not be just 2 bar 2, it will be multiple, it will be bigger, right?
Mm.
So that is the reason we get a reasonably considerably bigger pool, outcome of this pool layer, something like this, a bigger image,
Okay.
which will
Okay.
be once again passed through a kernel filter.
Okay. Okay.
So now
Okay.
we do not consider 5 by 5 image anymore, but we
Mm-hmm.
consider the output of this pool layer to this instead of image, 5 by 5 image.
Okay.
And these
Now, so
values
what
that
you're
we are
saying
getting.
is, like, first we in the pooling thing,
Mhm,
we first pass the activation function through a pooling
mhm.
kernel filter.
So sorry, can you please once again repeat it?
Okay. So in the pooling layer, what you're saying is, after we get the activation function through Relu,
Mhm.
which is like supposedly here you have written activation map, Relu
Yes,
activation.
yes. Mhm.
This we pass through a pool layer.
Yes, yes.
Yeah.
Mhm,
Which you said in this case is 2 by 2 and with a stride of 1.
mhm.
Now, after getting the output of the pool layer, which is 682 0, 682 0, we again pass it through a kernel.
Yes. But in this case, since we do have only 2 bar 2, we cannot really pass it through any kernel. Okay.
Yeah, yeah.
But in the real case, when you
In
take a
real
20 R
time,
bar 28 image and all,
mm,
so
mhm,
the feature map will be much bigger.
bigger,
Activation
of
map will
course.
be much bigger. So pool layer also will be much bigger. So
Okay,
once again, it is very much easy for you to pass through a kernel filter
okay,
of like again a 3 bar 3 or a 2 bar 2. You can do
okay,
that very easily. Okay.
okay, okay, okay,
So
okay.
once again, this process continues and we get once again one more pool layer.
Okay. So this also we don't need to do it, and like we don't need to physically do it. What we do is we pass a we can write a statement about it. Like we can pass it as a okay,
Yes, yes, we can do. So all these are basically parameters. That's it. Okay.
okay,
Which
okay.
which becomes so easy when we are writing a code. Okay.
Writing a program.
So
Okay,
that
okay.
becomes very simple. but it is important for us to really understand what is
Understand
happening.
what is happening.
Yeah.
Yeah, yeah.
Now, one more thing that you have to understand is that
Mm,
at this time we saw only one pool layer, but if our kernel filters is 32, then we get
mm.
32 pool layers like this,
Yes, yes,
right? So
yeah.
now all these 32 pool layers are once again like passed through our neural network. Once again, we do get this, okay?
Mm-hmm, mm-hmm,
So once this process is done, once the entire process is done, like what we do is we just convert, like we have 32 pool layers with the 62, 682, 682 value like that, okay?
mm-hmm, mm-hmm.
So all of them are taken into a single input array,
Okay, okay.
okay? Into a single input array. So the first value will be 682, the second value may be like equal to 0, third value may be equal to 75, fourth value may be equal to
So
40.
you form a array out of it.
Yeah,
Single
a single array
single
out
column
of
array.
this. Yes. This will be the input to our
Uh,
fully connected layer.
Fully collected. Okay.
So
These forms the features. Now they
yes,
form the feature. Okay,
yes.
okay.
So now by the end of the pooling, the feature extraction is already done. Because
Mm-hmm,
if we see that these values are really telling about very important values of my entire image. Okay.
mm-hmm.
We'll see it in live action as well, so that it will be very
Yes,
easy for
yes.
you to visualize as well. Okay. But once they
Okay.
form the part of this, then
Mm-hmm,
they will be connected to the fully connected layer. The fully connected layer, once again, this is very simple activation that
mm-hmm.
anyways we discussed what is dropout.
Yeah.
Just randomly removing certain connections, but it everything is the
Randomly
same.
removing. Just
Yeah.
to help in preventing
Overfitting.
overfitting and helps in generalization.
Yes. And then that is once again passed through our fully connected layer, that is passed through a software activation that is connected to an output layer.
Okay. So my question here is like whatever I've understood till now. So this convolutional neural network
Mhm.
is majorly because as we see is majorly used in image and face or like a picture kind of a
Image recognition,
recognition
computer
image
vision,
computer computer
computer
vision.
vision.
Okay,
Yes.
okay. So
Okay.
majorly in that like
Yes, yes, yes.
so whenever
Majorly.
whenever we get a whenever we get a problem or an issue of a image recognition
Mhm.
or visualization, so
Mhm.
we use convolutional networks only.
99% of the times we use only convolutional neural
Convolution.
networks because of their
Okay.
efficiency. But who gets better efficiency is the one who uses a better architecture.
Of course, of course, of course,
Simple, like that.
of
Okay.
course.
Now let us see really how a pooling layer works.
Okay, sure.
So how pooling has an impact on the final image. Okay.
Please. Yeah.
So for that we are and this is a program that I have already pre-written. Okay.
Okay, no problem.
So you need not worry about the program, but like it becomes so simple. But this is for your better visualization. Okay, this is not passed through any activations or a convolutions. This is just an image, and just to show if we get certain images and we apply pooling to that, what happens.
Okay.
Okay, and again, pooling is of multiple types. If we take only the maximum number out of that pools, it is called max pooling.
Okay. Okay.
Okay, if we take an average of all the pixels and give something, it is called as an average pooling.
Okay.
If we take only the least number and put it, it is called minimum pooling.
Okay. Okay.
Okay,
Okay.
so
So
now
right now, what we did was maximum pooling because we
yes,
took the
yeah,
maximum number.
maximum of the number.
Okay. Okay.
Are you able to see my screen?
Yeah.
You can see a image of a person.
Yeah.
It's me.
That's your.
Yes. So first, this is a normal image. The first thing that we do is whenever we deal with image processing kind of operations, we
Mhm.
generally convert it into grayscale.
Okay.
Okay, that is a common activity that we do. Okay,
Mm.
so I'm converting it into a grayscale, and how here it appears.
So how did you do that? Like, how do you convert it into grayscale?
There are inbuilt functions. I'm going to
Okay.
show it to you. That
Okay.
that's just again one line of code. It is not like a
Okay.
huge task.
Okay.
One
Okay.
line of. So we use OpenCV, which is a library
Mm-hmm.
which has
Oh
its
yes. Yeah.
yeah, which has its method called cv2.color underscore bgr to gray.
Okay.
That is
Okay.
a method that it uses, and we have to pass the image as an argument. The moment we pass image as an argument, it converts that image from bgr to gray color.
Great. Okay. Okay.
So now I have converted the image into a grayscale,
Mm-hmm.
and
Mm-hmm.
now I'm applying max pooling. Okay,
Mm-hmm.
there is some logic that I have written behind. That is a different story.
Okay.
But before
So
that,
we are skipping all those steps coming to pooling right away.
yes, yes,
Okay.
okay, because just I wanted to show what pooling has an impact on.
Mm-hmm.
Okay, now the original image is a 496 bar 390 pixels, 496 pixels in height,
Mm-hmm.
396 pixels in width.
Mm-hmm.
And once again, this is once again a very important thing that we should always remember.
Mhm.
Whenever we, in general terms, we speak
Mhm.
about images, we
Okay.
tell the dimensions in terms of width and height. First, we say the width, and then we
Mhm.
say the height.
Okay. Width and then the height.
Height. That is generally how we speak.
Okay. Okay.
So we
Okay.
see an image, we say 5 by 7 inches, 5 by 7 photograph. Let us say a
Okay.
generic photo.
So 5 is the width and 7 is
7 is
the
the
height.
height. That is how we
Okay.
generally
Nomenclature. So this is a
yeah, that
normal
is a normal
nomenclature.
thing. But when it
Okay.
comes to image processing libraries, first is the height, next is the width.
Okay. 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 Okay.
Okay. Any guess why that can be so? Or do you think that they just
Uh,
want to make it complex? That's why they did it.
there must be some concept behind it. Majorly because most of the images are have like the y-axis. They have they're
No,
literal. No,
no,
no.
no, no.
Okay.
The reason why did they do that such a kind of operation is because
Mhm.
whenever we pass an image to any of the libraries,
Okay.
all of them convert the image into matrices, a matrix of numbers.
Okay. Okay.
Whenever we speak about a matrix, we always say the rows and then the
Rows and
columns.
yeah, yeah,
Rows are nothing but in height, columns
yeah.
are nothing but in the width.
Width.
So
Yes.
first we say rows, which means height, and then we say columns, which is nothing but the width.
Okay. To match that up, we
Yes.
use this nomenclature.
Otherwise, this will be a huge mess because all the matrices calculate only on rows and columns kind of thing.
Yeah.
So if we suddenly reverse it, it takes
Mhm.
a huge thing once again to convert every column into row and
Into
then
row.
do that operation. So that's
Yeah.
the standard practice that we always give a height and a width. Okay.
Okay. Okay.
That is the reason why when I say 496 bar 390 pixel image,
Mhm.
it is 496 pixels in height, 390 pixels in width.
Width.
And now
And 3 is the BGA,
the RGB thing.
RGB thing.
But though it shows a grayscale image, I printed the coordinates when I first showed you the original colored image.
Yeah. Yeah.
That's why it is showing as 3.
It's
Okay.
3.
Yeah. Now once again it is converted to NT grayscale.
And when it becomes like gray, it would
It
be
becomes
2.
1, 1, 1, 1,
1.
1.
Okay.
Because it ranges just from 0 to 255.
0 to. Okay. Yeah. Yeah.
Only one channel.
Arrays. It becomes
Yeah.
an array like
Yes.
because array
One
takes
channel.
numbers from 0 to 255. Yeah.
Yes. Yes. Okay. Now I close this. So now do you really want to see if I apply maximum pooling? Okay.
Yeah.
So what I did is in this entire image, I didn't
Mhm.
apply any convolution. I didn't apply anything. What I
Okay.
did is I went to the entire image, took
Mm-hmm.
every 2 bar 2 like pixels, okay,
Mm-hmm.
and then I took the maximum out of everything, and I
Okay.
reconstructed this whole image.
Okay. Okay.
So I went to every 2 bar 2 pixel,
Mm-hmm.
okay, and took the
Mm-hmm.
maximum out of it and put it in a new image.
Okay.
So
Okay.
that's how I reconstructed my entire
So
face.
what you did was you took 2 by 2
Pool size.
pool yeah like metric size,
Mhm.
and then you took the maximum out of those 2 by 2 matrices and you reconstructed the image.
Yeah. So it's like this. I'm opening with paint. Okay, this is my image. So I
Mm-hmm.
first take the first these 4
Mm-hmm.
pixels. I take the
Mm-hmm.
maximum out of this, and I
Mm-hmm.
do this again. I do this again.
They'll all be zero, like
Yeah,
because
but
they're white.
it'll matter when it comes to this part. My important
Mm-hmm.
face features, right?
Mm-hmm.
Here there will be some numbers. So
Mm-hmm.
based upon that, I once again reconstructed the entire image. Okay.
Yeah.
When I do this, do you want to see how my face appears when I do
Sure.
maximum
Sure. Sure.
pooling?
Sure. 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 Oh. Okay. Okay.
And you can see it is compressed
Yeah.
because out of every 4 pixels, I take only 1 pixel.
One. Yeah. Yeah.
So obviously our image dimensions have reduced.
Yes. 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 Yes.
Okay.
Yes.
And if
Mm-hmm.
I do an average pooling, because since it takes only the maximum of the images,
Mm-hmm.
maximum of these 4 pixels, you can see my eyes completely white
Right.
because it is trying to take only the maximum pixel. It is trying to ignore
Yeah.
that, what I can say, black pixels,
Black pixels. Yes.
right?
Yes.
Like it the same follows for all this entire image. Okay. If I take an average pooling,
Mm-hmm.
okay,
Mm-hmm.
it appears like this
Okay. Little
because it,
blurred.
yeah, it takes an average of all these 4 pixels and try to put it here.
Try to put it here. Okay.
Yes.
And it is also compressed. This is also compressed.
Mhm. Yeah. So,
Yeah.
and finally, we'll
Mm-hmm.
take the minimum pooling. Okay.
Okay.
When we take a minimum pooling, when we
Mm-hmm.
take a min pool, see how it appears.
Okay.
You can see it is much darker because when we say
Mm-hmm.
minimum pooling,
So eyes are
minimum,
also black.
yeah, because it takes only the least value. Least value tends towards to be 0. 0
Zero.
means a black pixel, right?
Black pixel. Yeah. Yeah.
That is the reason why it tends to be more of blackish rather than the whitish thing. Okay.
Yeah.
So by this, like by this visualization, I feel that you have a better understanding about
Yeah.
what
Yeah.
pooling
Yeah.
is,
What it exactly is doing.
what it exactly does, right?
Yeah.
So
So
no,
maximum is more towards the right side,
yeah,
meaning average is in the middle,
middle.
and then
Yeah, average is taking those pool
the
size
darker,
and
the
averaging
black.
all the images within that region.
Mm,
Okay,
mm,
that is this. So now once we get this, we do
mm.
something called as flattening. Flattening converts all of these into a single array of numbers.
Okay.
And
Which gives us
a single array,
like a in like a
like an
input
input.
layer.
Yes,
Input layer.
for our fully hidden, I mean collected layers. And from
Mm-hmm.
there, they will be connected to further layers, and finally we get the final output. Okay,
Okay.
and that is how. Once again, let us go back here. So now, do you think our entire architecture is now clear?
Yeah.
That is how we are going to apply convolutional neural network. Okay.
Okay.
So in the next class, I want
Mm-hmm.
you to really work upon a data set called Cipher 10.
Cipher 10.
Yeah, we have downloaded Cipher 10 already
Okay.
in Keras. So if you see from keras.datasets, you can import Cipher 10. Okay.
Cipher. How is it spelled out? CI.
CIFAR 10.
Cipher 10.
Yeah.
Okay. 10. Cipher
Yeah.
10.
Cipher 10. Okay.
Okay.
This Cipher 10 is like, I mean, an image classification of 10 images. Like it can be automobile, birds, frog, deer, cat, blah, 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 ship,
Okay.
dockyard, etc. It is
Mm-hmm.
like, I mean, the final output classes are 10 classes, similar to
Yeah.
our MNIST.
Okay.
But MNIST is a 28 bar 28 images, right?
Yes.
Cipher 10 are 32 bar 32 images.
Okay. Okay.
Okay.
Bigger.
And also, yeah. And also, MNIST is a one color channel.
Yeah.
Cipher 10 is a three color channel.
Okay. Okay.
It's an RGB image. But
RGB.
doing a regular neural network is just the same. We multiply all of these things together. So the training images are 50,000 images.
Mm-hmm.
Okay. And we are reshaping it to 32 into 30 into 3. So that will be
Okay.
the 3072. So our training images will be of the size 50,000 comma 3072.
Mm-hmm.
Testing images will be 10,000 comma 3072.
Okay. Okay.
I want
Okay.
you to I want you to do is just to apply a regular common neural network, not
Okay.
all these convolutions and all. You just apply
Mm-hmm.
a regular neural network.
Okay.
So
On a
all
cipher.
these, yeah. So all these 3072 will be inputs,
Yeah.
because earlier in an MNST 784 are the inputs, right?
Yeah. Yeah.
On a Cipher database,
Because that was a simple image of
yeah,
one.
it is a 28 comma 28 comma 1,
Mm-hmm.
one color channel.
Yes.
Since it
One
is of
color
three
channel.
color channels, it will be 32 into
784.
32 into 3. That is 3072. Okay.
Okay.
So
Okay.
all these are 3072 inputs, and the
Okay.
output will be 10 classes.
Okay. Okay. Okay.
Okay.
Okay. Yeah.
So can we just prepare a regular common neural network? And in our
Mm-hmm.
next class, we will try to apply convolutional neural networks onto that and see the difference
Perfect.
in terms
Perfect.
of accuracy. Okay.
Yeah.
So
And please send me the recording of today also.
I will do that. I will do that. Yeah, I'll do that. Okay.
So you're going for work today or at home?
Most probably at home.
Okay.
Yeah,
Okay.
I'll be at home today.
Have fun then.
Yeah. Thank you, and have a great day, you too. Bye
You too.
bye.
You too. Bye.
Thank you. Bye. Bye.
Bye.